I was saying that let's pick this surrogate function and do whatever I said in my previous lecture. So at case iteration, the value of them should be equal, Ci, and the slope of both of them, I mean the original and the approximation, should be the same. So at point xak is equal to 2 xik. So this becomes xik wik xik squared plus cik. And the sign of xik, p xik, is equal to 2 wik xik. So from this equation and this equation, from 13 and 14, we can get quadratic majorization function. So what is our quadratic majorization function given at case iteration we are at point xik? So this one is equal to p over 2 xi case iteration p minus 2 xi squared plus 1 minus p over 2 xik p. What if this one is 0? What if this one is 0? So u of xi at 0, some people say, let's handle this problem with this. But this makes xik plus 1 converged too soon. But we didn't go at good places. So that's not a realistic solution. So some people say, okay, how about this one? Some people say, how about xik squared plus epsilon p minus 2. So they call it a damping approach. But none of them are good. So the best solution is just locally we say, okay, ax2 is nice if we are in an epsilon neighborhood. But if we are not in epsilon neighborhood, then let's get this one. But because at the junction, I mean epsilon, x is equal to this, we want to make it differentiable. We want to make it the same thing, both continuous and differentiable. So in order to do that, a epsilon 2 should be equal to gp epsilon minus b. Also, there also 2a epsilon should be g prime of epsilon. So we can say that it should satisfy in the epsilon neighborhood, it should satisfy this. And if it is not in epsilon neighborhood, this is proper because there is no problem with differentiability at epsilon point. And also it is good. And so for if your surrogate function is like mine, which is this one, my favorite, then we have the same function, which is in epsilon neighborhood is equal to p minus 2 x squared if we are epsilon neighborhood. And if we are not in epsilon neighborhood, it becomes xp minus 1 minus p over 2 epsilon p. And so the idea is like this. You have a very non-differentiable, and you approximate it with a very smooth, gentle, but like this. So for epsilon 5 is like this. And this is epsilon. And so finally I can say that using smooth approximation, we want to maximize x transpose ax minus rho gp epsilon xi subject to x transpose bx equal to 1. And we noticed that at case iteration, this becomes at epsilon neighborhood. And if it is not in its epsilon neighborhood, it becomes xi at point k, p minus 2. So we omit C because it is irrelevant for our maximization, majorization, minimization, minorization, maximization, and we correct the quadratic regularization. So we repeat. We first compute WK, and xk plus 1 is equal to leading generalized eigenvector of matrix pair A minus rho diagonal WK and B. But I tell you, the drawback is that matrix factorization is expensive. And even if you want to transfer the standard eigenvalue problem, for example, Cholesky decomposition of B, it is very expensive. So solution is first of all, let's say that we have a Rayleigh quotient. We want to maximize this Rayleigh quotient, x transpose A tilde x transpose bx. So what do? We just calculate the gradient of that, and you want to do a gradient ascent method. So at xl, this is 2 over xl transpose bxl, and this is scalar, and this multiplied by A tilde xl minus r of xl multiplied by bxl. So this is your residual. It becomes 0, then you've got your optimal point. So your direction, let's say, direction at L is use a preconditioner to accelerate convergence. So this is another issue. It is a preconditioner We do it in fluid mechanics. We do it in quantum physics. We do it in machine learning. We do it in portfolio optimization, in investment theory. So I've seen it in several places. I've seen it in aerospace engineering as well. So preconditional, we use it. And PRL at XL, and then X is equal to XL plus, because it's steepest ascent. Tau is your how much do you want to go in direction of RL. So preconditioning is an important technique in iterative methods for solving large-scale linear equations. For example, the widely used precondition conjugate gradient method. It can also be used for eigenvalue problem. For example, your P diagonal, it is a diagonal. It becomes, take this one, for example, plus diagonal of A and inverse of this, and otherwise. So we use this if, for example, rho WK over norm of diagonal of A is greater than 100. So we apply precondition only when some elements become relatively large. Otherwise, it's we don't care about it. So don't care. And in the next lecture, I want to talk about Laplacian operators because it is relevant to my paper. So I will talk about Laplacian operator first from the physical point of view, how it appears in physics, in wave equations, in heat equation, in many equations. And I will show that it is the minimization of it to decay energy. And I will extend it for a discrete Laplace operator because we are on graph. And you will notice that manifold regularization becomes very important if you are dealing with semi-supervised learning. It means that you have some labeled data, not very much, very few of them, but you have huge number of unlabeled data. So you have to care about both of them. We care about it with a kind of Laplacian regularizer. So we only care about smoothness on data manifold. And there are many methods like Laplacian regularized least square. They call it LAP RLS, or also Laplacian support vector machine. You know, support vector machine, I've talked about it in several videos, but you can use a different you can use a different regularizer, because you can, all of these things can be understood if you care about semi-supervised learning. I think Jubin Rahmani had a YouTube video about that. He is in Cambridge or USA, I don't know. But he has talked about it in a very nice, beautiful video. It's about semi-supervised learning, and Jubin Rahmani creates some graphs and try to show the intuition behind that and why semi-supervised learning is important and how you can deal with that. And I will talk about it in several lectures. And finally, I don't know if I talk about diffusion map. It's a very modern method. It has some limitations, but diffusion maps is a really interesting idea that I will talk about it. But I think it's time to stop it here.